Hello everybody, I'm Nick, and today we're going to try to describe link budgets on satellites going out to GTO. Now the way I typically do this is I set up a spreadsheet, and on the far left column, the C column, I put parameters such as the frequency, the data rate, and things like that. Now some of these parameters have numbers with them, and some of these things require calculations. So in the D column, we'll have the known values, and if we have to do some calculations, I stick that in the E column. And in the F column, I try to put the sources where it comes from or a formula. So let's get started. I want to do this quickly. It's kind of tough. So one of the things that as an engineer, one of the inputs, you have to decide what frequency you want it on. And it turns out from experience, 0.145 gigahertz is one that's allowed by the FCC and is a good first choice. The next thing as engineers you have to decide is data rate. And through experience, 1200 is a pretty good compromise. Now, once you decide the data rate, you also describe the type of modulation, and typically we choose frequency shift keying. Shannon tells you that you probably need about 3,000 hertz of bandwidth to do that. There are some trade-offs, and you can do some things to reduce that, but that's beyond the scope of this video. Now, you have to point this antenna to the satellite. So, and the satellite will traverse the horizon from 0 degrees in elevation up to 90 degrees when it's right overhead. Well, because this thing tends to be at the equator, it may not get overhead. But at some point, you have to decide where you're going to point the antenna, and 30 degrees above the horizon is a pretty good first choice. Now, this happens that when you have an antenna at 30 degrees, it's looking out into deep space. And there are noisy objects out there in deep space, but most of the noise coming from an antenna at this frequency is terrestrial and local. And through experience, a good number is 1,000 degrees Kelvin. So we will put that in our calculations. Now, one of the choices you have to make is that it turns out you're going to want to have a low noise amplifier on the receive side. Here is one of the things you can choose. Now, the state-of-the-art low noise amplifiers that are not cooled can typically be about 1/4 dB. They're very expensive, but 1 dB is a pretty good compromise. And let's start with 1 dB of noise figure. That's the noise that the amplifier puts in. Now, once you've decided the noise of the amplifier, we choose to work in equivalent temperatures. Remember that you can represent noise in an amplifier by its equivalent temperature. So here's the formula to convert noise figure into noise temperature. Now, one of the parameters we're going to need is the total system noise. That is essentially the summation of all the noise sources. Today in this discussion, we're only going to account for 2 pieces of noise. The noise basically coming from the antenna and the noise in the amplifier. The sum of those 2 numbers turns out to be 1,075 degrees Kelvin. One of the other parameters that we need to consider excuse me, is the distance between the satellite and the receiving station. Now, when you're out at GTO or geosynchronous altitudes, it turns out that this this distance turns out to be approximately 22,000 miles. Remember, this orbit is highly elliptical, and at some point may get as low as 200 miles. but we always design on the worst case. Today we'll talk about 22,000 miles. Now, as an engineer, you have to decide to transmit power on the satellite. This is a key component, and most satellite engineers tend to describe all measurements in dBs, or dB reference to 1 milliwatt. So it turns out that 1 watt is equal to 30 dBm, which is a pretty good choice to put on a satellite, especially one as small as we have. The next thing as an engineer is you have to decide or design in the gain of the antenna. And it turns out that it's very difficult on a small satellite, the ones we use, to make the antenna perform equally well in all directions. And if that in fact happens, the gain on that antenna turns out to be 0. We get essentially no gain from the antenna at the satellite. Now the next major component is the free space loss. That's the loss that occurs because the distance between the antenna of the transmitter and the antenna of the receiver is large. And you have some anecdotal feeling for this. If you have a satellite, if you have a flashlight and you shine it on an object that's say a foot or two away from you, it appears to be bright. If you shine it on an object that's say 10 or 15 feet away, it gets dimmer. And if you shine it on an object that's say 100 or 200 feet from a flashlight, it gets so dim it's undetectable by your eyes. Well, we have the same thing in space, and as we every time we increase the distance on the satellite, we lose 6 dB of power, and that is and we describe, and the formula to describe this is 20 times the log of the distance in miles plus 20 times the log of the frequency in gigahertz plus 96. Plugging those numbers into our length equation that's out at 22,000 miles, the loss between the antennas is 166.7 dB. That's a lot. If you start out with 1 watt on your satellite, by the time you get to the ground, you've got a fraction of a milliwatt. So we need to do some things about that. Now, the next thing that, as an engineer, you get to choose the gain of the receive antenna. It turns out that 14 dB over an isotropic source is a pretty good choice, and that's the size of the antenna on our ground station. Now, if you want to increase the gain of the antenna, you double its size. So if you put up antennas that are twice as large as the one on the engineering building, you gain another 3 dB. That's a number you choose. So now we can now calculate how much signal we have when we point an antenna at our satellite. So we start out with 30 dBm or 1 watt. Our antenna doesn't add or subtract any power, and we lose 166 dB traversing 22,000 miles. But we have a big antenna, and we gain back 14 dB in that. So the amount of signal reaching the ground is just the algebraic sum of those 4 elements that we described above. It turns out that turns out to be minus 122.7 dBm. That's an absolute power at the output of that antenna. So now we've done half of the equation. We have calculated the amount of signal that satellite sends to the ground. Now the next thing we have to do is to figure out how much noise is on that satellite. Well, it turns out that we know that if we know the temperature of an object, we know how much power it emits. This was described in some equations by Planck. Incidentally, he did that a couple of centuries ago. So it turns out that the absolute power coming from an object that's warmer than that's warm puts out 10 times the log of Boltzmann's constant times the bandwidth in hertz times the temperature, the absolute temperature in kelvins, and the formula highlighted in this deal is the decibel equivalent of that. So now if we know the signal and now we know the noise, we can now know the signal to noise ratio. And that is simply in the log form is the algebraic sum of the signal minus the noise. It turns out that if you do this calculation, as in this spreadsheet, that turns out to be 10.8 dB. So we now know that the signal noise ratio on our link is 10 dB. Now, here's where Shannon comes in and the modem design. So once we have a signal that's embedded in noise, we have to convert that into digital form. And it turns out that if we are careful in our design, our modem design, and this comes from some modem curves, we need 7 dB of signal noise to produce a bit error rate of 10 to the minus 6. That means that if we present that modem with a 7 dB signal noise, we will drop only 1 bit in a million cent. Now, if we take how much we have to how much we required, the excess is called the link margin in dB. And it also turns out that if this system is to work, this number has to be greater than 0. So, guys, this is a simplified version of a link budget. We've left out a few major losses. We haven't talked about the polarization losses. That remembers that this satellite is kind of tumbling out there in space, and that what happens is that it gets misaligned with the antenna and creates additional losses, which could be as high as 20 dB, which is significant. And if we lose 20 dB, we lose the circuit. Also, we haven't accounted for other things like the feed line losses and other things. But this gives you a start onto what we're up to. And I'd like you guys to watch this thing and we can have some further discussion.